Now we now come to the experiment of Lloyd's mirror in microwave propagation training system. To set up the equipment, we set up the transmitter and we set up the receiver, both in the same polarization at a distance of approximately a meter between the two, and we keep them equidistant from the goniometer, and we keep a metal reflector at a perpendicular direction from the goniometer, so that the metal reflector is at a perpendicular to the receiver and transmitter. Now we observe the signal. The signal right now is 57.4 dB microvolts. Now in the propagation, there is a signal which is being transmitted directly from the transmitter to the receiver, while a small part of the signal is also being reflected from the metal reflector and arriving at the receiver. So at the receiver there is an interference pattern from the reflected signal and the direct signal. Since the direct signal is quite large in comparison to the reflected signal, but still there is an interference pattern being formed. Now as we move the metal reflector towards the goniometer, the path length of the reflected signal changes, and it changes the interference pattern perceived at the receiver end. So every few wavelengths movement of the metal reflector will change the maxima or minima of the pattern at the receiver. Now we observe the signal strength, and at the same time we keep a note of the reflector position. So for say the reflector position of 22 centimeters, the received signal strength is 57.6. Now as we move the reflector towards the transmitter, we need to make sure that the reflector is always perpendicular and there is no change in the direction of the reflector. Now I am moving the reflector. You will see that the reading is going through a maxima here. It is increasing, and then it will pass through a minima gradually. Now it is passing through a minima. We will take a note of the readings of the minima, as most of the time the minimas are well defined, and by measuring the difference in the two consecutive minimas, we can arrive at the wavelength of the electromagnetic wave in this particular experiment. So this concludes our experiment for the Lloyd's mirror. Now we come to our experiment of Fabry-Perot interferometer. For performing an experiment of Fabry-Perot interferometer, we'll put two partial reflectors along the path of propagation of the microwave signal. Now the transmitter is transmitting a microwave signal, and it is being passed through two partial reflectors. These are transmitting most of the signal through, but a small part of the signal is reflected back. Now by virtue of this arrangement, a small part of the signal, if it arrives here, a small part of it is reflected back again, and a small part of it is reflected back from here again, and gradually it goes down to zero. So at the receiver end, what we are watching is an interference pattern of different wavefronts arriving at different times. So as we move the position of these two partial reflectors, we can calculate the wavelength of the electromagnetic wave. If the distance between the two partial reflectors is a multiple of the wavelength, of half the wavelength, then we will have a maxima at the receiver as the signal will die down. Or if in case the distance between the two partial reflectors is not a multiple of the half the wavelength, then the signal received at the receiver would be different. As you can see, we will change the spacing of the partial reflectors and we can see a change in the receiver reading. So that concludes our Fabry-Perot interferometer.